Okay, so now what we want to do next, we do know what is our objective, this j function. And what we want to do, we want to maximize it, or basically we want to minimize its negative, right? Well, if you want to maximize the objective computed in terms of the output of a neural network, what you do, well, you have no way but using a gradient-based approach, right? Basically gradient descent. So what you're going to do, you're going to start by gradient descent. So it means that you start with some theta. This is the parameter you have. You compute the gradient of this objective, and then you just move in the opposite direction of the gradient. Since your objective is already minus that j, it's going to be plus. So this is what we call a gradient ascent, not descent, right? You move in the direction of gradient itself, not the negative one, right? OK, so we want to do this. So the only challenge here is that we need to figure out a way to somehow estimate this gradient out of what we have in practice, right? Out of the policy network, the environment that we can only sample from, and so on, right? So that is the whole challenge that we have here. So we want to do the gradient ascent, and we need to know that gradient, right? OK, so let's just start writing down the gradient. So we talked about this. This j was, let's get back here, j, this objective function. This guy is the expected sample return on the distribution of the trajectory, right? And that distribution of trajectory is explicitly given to us in terms of the policy. OK, so we're going to go on that one. So we want to take the gradient here. Now, if I want to take the gradient, where does gradient go in these terms? The p one, right? It's going to go to the density term, right? Because the g term, the sample return, does not depend on that one explicitly. So this is going to be my gradient, right? Everybody agrees, right? Now, if I want to write that guy down, then this means that I should take the gradient of all of this product, right? And it seems a bit complicated, right? But there is actually a very efficient way to do that, right? So we can do it much easier by a simple trick. So the simple trick is what we call it log derivative trick. I mean, it's not a trick really. It's just a high school math. So just to if I have this function f, which is a function of x, okay, and I want to take the derivative of this guy with derivative of fx, with respect to x, what can I do? I could say, okay, instead of f, I compute the derivative of log of f, right? What would it be? What is the derivative of log of f? Is 1 over f times derivative of f, right? So it's going to be 1 over f itself times derivative of f with respect to x, right? Now I'm going to take this guy. I write it down here, right? So derivative of f is f itself times the derivative of its log, right? It's basic math, right? You can do it in multidimensional case. Instead of derivative, you just put gradient, right? OK, so that's just the whole derivative trick. So if you have a function of parameters theta, then the gradient of that function is basically the function itself times the gradient of its log, right? And you can guess what I'm looking for log. One basic reason is that my f is multiplication of lots of pi terms, right? If I take log, then it's going to be a summation. But this is not the only reason, right? OK, so I can do that, and then I can take this one and use it inside my expression. So I wanted to compute this gradient, right? The gradient of p, the density of that trajectory. Instead of that, I'm going to write it down as the gradient of the trajectory, right? Sorry, the probability of the trajectory times gradient of the logarithm of the trajectory, right? Everybody's cool? And now I can just sort things out. It's going to be this one. Now you look at the final expression. What is that? Is this any specific operation? What operation is it? Yes, go. It's a gain expectation over trajectory. Right, perfect, right. So this is expectation with respect to this P of trajectory, right? Because you have one term, which depends on trajectory, times the probability of that trajectory, and you are integrating over that, right? So this is basically expectation of your sample. So it's G and the sample return times gradient of the logarithm of that pi term, right? Expected over the trajectory. Now, it's true that computing this integral is complicated, but what about this expectation? Can I have any computational way to compute that expectation? And for now, say that I do know what is log of p. I do know what is that gradient. Can I do it? Yes, go ahead. Perfect, right. You just sample lots of trajectories, right? You're expecting, taking expectation over trajectory, right? And the only thing that you need to do is to just sample with the same distribution. This is not a hard thing, right? You just sample with one star distribution for your state, and then you play with your policy, then you're going to get one trajectory, right? That trajectory is coming from that distribution, right? This is one sample. So this is one of those G and gradients that you want, right? You just sample lots of them. You average them by Monte Carlo. This is estimate of this expectation, right? Okay? So we are getting to the point where we can estimate things, right? So this is the expectation that we want to compute. That one, I mean, this integral in general, if we think of a general case for tau, like giant, massive tree, this is really hard to compute, computationally impossible. But this one, we can estimate it. We have a way to estimate it, right? OK, that's it. Now, the key point here is that you might say, OK, that sounds nice, but what about this log of pi, right? This guy is also problematic here, because it depends also on this p-value, which depends on our environment transition function, right? That p of pi theta depends on your transition in the environment as well. So let's open that guy up as well. So what I want to do, I have this guy, right? This term that I have here is basically the term we collected as the density of the trajectory. The chance of you start with S0, then pi, the policy that you play action A1, right? And then the transition, then again pi, again transition, and so on towards the end, right? So this is the term that you have. If I just apply log on this guy, what's going to happen? Log is like the magic wand, right? It's going to just break everything into summation, right? So I'm going to have log of PS0, summation of log of all of those pi's, right? And summation of log of all of those p transitions, right? Everybody's cool? Now, this guy depends on theta, the middle term, right? The side terms, they do not depend on theta, correct? If I take the gradient with respect to theta, what's going to happen? These guys are going to be 0, right? And this is basically what I need, right? I need the gradient with respect to my parameters. I do not need the log itself, right? So what I'm going to do, I'm going to take the logarithm here. This guy is going to be 0. This guy is going to be 0. This is the only guy that is going to show up, right? Can I compute this one? What is pi? My policy network, right? I have access to this, right? I can compute those values, right? Pi theta is my neural network, right? I can work with that. So I can compute that. And I didn't know these terms. I don't care anymore, right? Because they are not showing up in the gradient, right? So the thing that is going to happen, the gradient of my log probability of the, or log likelihood of the trajectory is basically going to be summation of all of these gradients, logarithm of the policy over the whole trajectory, right? So you need to go over your trajectory. You say, OK, I started at S0, and I did action A0, right? Then you put S0 and A0 in the input of your neural network, right? It's going to go and compute your pi, right? Once computed your pi, you just backpropagate. I mean, first you compute log, of course. And then you backpropagate. then you're going to get the first term, right? Then you just put S1, A1. Again, you go over the neural network, you get the output, you take log, back propagate, second gradient, right? And so on until the last one, right? So this one you can definitely do it computationally, right? And then if you just complete the loop, then, I mean, the whole gradient term that you want, you can actually compute it. So now don't think about one particular trajectory. Say I have a random trajectory, so I randomly sampled one initial state and played with my policy. Then I'm going to have this gradient term, which is again random. And the reason of randomness is simply because of the actions and state that I have randomly, right? So this is my random gradient term, and then I replace it here, right? So this guy is the sample return. This is the sample log likelihood or gradient of the log likelihood of the trajectory. And I can compute both of them, right? Everybody's clear? Now, this guy is not computationally feasible because the terms here inside, I can do it by backpropagation. And then this expectation, I can simply approximate it, estimate it by sampling, right? So this means that I have a way to estimate the gradient of my objective. Now I have the gradient of my objective. I keep on moving in that direction, right? And my policy network is going to get trained to optimize or maximize the expected value. Hopefully it's going to get to the optimal policy. Everybody's clear? You got the idea? So that's it. So this sample return is what I'm going to sample over my trajectory. This guy is again given by my policy network on the trajectory. And I just need to sample multiple trajectories, use Monte Carlo to average that, right? And this is going to be the policy gradient approach, right? So if I have this particular trajectory, then I can just sample k different samples from it. And then for every single sample, I do have the sample return, right? What is sample return on the trajectory? I simply add up every guy here, right? That is a sample return, right? I have this one. And then I just, as I told you, I give S0 and A0 to my policy network. I do backpropagation. I get the first gradient, right? S1, A1, backpropagation, second gradient, and so on till the last guy. So I'm going to have all of these t different gradients, right? And I add them up, right? Now I have this sample gradient. I have the sample return. I multiply them. And this is one sample, right? And if I have k different samples, then I'm going to average over those different k samples. This is an estimate of the gradient that I want. Now I update my parameters with this sample or gradient estimator, right? So I'm going to say that whatever the guy was, I just add it up with some learning rate towards that direction, and I keep on updating, right? Everybody's cool? So that is basically the most, say, naive or simple version of the policy gradient that you can do, right? So here, as you see, basically in this particular case where we are using Monte Carlo, you don't really need to know the value network at all, right? You just work with your policy network, correct? You have a policy network, you sample from that policy network, you build trajectories, you get Monte Carlo estimators of those trajectories, those G, right? And using that, you just update your policy network. You keep on doing it. If you do it forever, then eventually this guy is going to converge to the optimal policy if your network is complex enough to be able to learn the optimal policy. Questions? No question? Yeah. No, because what average you mean? This average? This average? No, I don't do that. Because when I am sampling, that is going to happen by itself, right? When you are using Monte Carlo, if you have a random variable, for example, a binary random variable, right? And say 1 happens with probability 80%, 0 happens with 20%, right? You would not weight anything when you want to do Monte Carlo, right? You just sample. But if you sample 100 times, 80 times you see 1, 20 times you see 0, right? And then you add all of them up. It's going to be 80 divided by 100 is 0.8, right? This is the same thing happening, right? This tau k that I show here, right? This guy is happening more for the trajectories which are more likely, is happening less for trajectories that are less likely, right? So you have only 2 possible trajectories, right? If one of them is happening with probability 80%, then this means that when you sample 100 trajectories, 80 times you're going to see the first trajectory, 20 times you see the second trajectory, right? So you don't need to weight anything, right? You just sample enough, and then you average that. And then law of large number tells you that this is going to be your expectation, right? It's clear?
Yes.
Yeah.
Is there any formula that we can think of to sample enough?
Oh, again, you can guess that we really need a high number of samples, right? Because we have giant trajectory space, right? It's not only state space, action space, right? Space is the whole trajectory, right? It's giant, but then we're going to get into ways that handle that issue, right? But at the end of the day, you cannot rely, right? You just randomly sample something, use those samples to just update, and you hope that the model is complex enough and the environment is like simple enough that they're going to match at some point, right? It's exactly like deep learning, right? Because your, for example, image space is giant, right? You never have enough number of data to really approximate the distribution of that stage, right? Sorry, image space, right? You can never, even for MNIST, we can never find out the right histogram, right? Because it's giant, right? But for goal of classification, you can collect enough information from those few samples that you do the right classification, right? So here is the same thing. I mean, definitely we are not able to explain the whole trajectory space. That is beyond our ability. But maybe finding out the optimal policy is not that complicated. So it does not need the whole information, right? And you can think about that, right? Like if I want to get to the door, right? Like this space is giant, two-dimensional space, right? Number of states that I have is infinite, right? But finding out the optimal policy to get to the door is not a very complicated thing, right? Every time I just take the shortest distance, right? That's it. Questions? No question? Okay, so obviously this guy is Monte Carlo. Monte Carlo is not sample efficient. It means that if I want to do this, I need to wait for k different trajectory samples. And after that, I should update. This is something that we do not like. What do? We do not do anything. We basically just update after every single sample, right? This is what we do because that's it, right? We can do nothing about that. So we basically use stochastic gradient descent. And how we can do it? Basically just we sample one single trajectory. We compute this guy, right? And then we update with that single sample, right? So you update sample level, right? And the main reason is that, well, sampling is complicated enough that you cannot wait for multiple samples, right? So that's going to be the policy gradient, version 1, the most simple policy gradient that you can think of if you want to just train one policy network on your environment without using anything else. So what you're going to do, you're going to start with one sample, right? You just sample one trajectory. Once you have the trajectory, this guy is containing enough information that you can compute or estimate some gradient, right? So you're going to compute the gradient of logarithm of pi here, right? You're going to compute this guy. This g is simply the summation of all of the returns you get. If you have a discount factor, of course, you just include the discount factor as well. It's just the sample return. And then you update with this sample. You go on for the next time, right? Sorry, next sample trajectory, and so on. Each time you update your theta, and hopefully it's going to converge, okay? Now, this guy, does it sound like something new? Yeah. It's actually not new, okay? So this is modified version of what we know it as reinforced algorithm. But this guy, Williams. Do you know Ronald Williams? You don't know him? What? Ronald Williams, you should know him. Just check his name, okay? Just check who he is. All right, he has done lots of contributions. So this is reinforced algorithm, basically, and it was established in 1992. So it's not exactly the reinforced algorithm. The reinforced algorithm is this guy. And can you detect, this is like this test in the magazine, can you check the difference? How many differences you can find? Now, okay, just look at it here and then compare it to this one. I mean, one line is just dropping, right? Just tell me what is the difference now. It's G, right? The sample return. Here I'm just writing GT. Here I'm just writing the whole return of the trajectory, right? Why do I have it here? Because in our analysis, we always work with the complete trajectory, right? That was what came out of our analysis, right? But then, if you implement it with this one, this means that at every single time, you don't use the complete one. You just use the sample trajectory of that time. Like when you get at time 1, you do not add up R1 anymore. You just start from R2 going on. Okay? That is the only difference. If you do this one as well, this is going to work, and actually it's going to converge a bit better. This was what William showed. And you might say why this is happening. Well, the key point here is what we call it the policy gradient theorem. And the policy gradient theorem says that that G you see there, even if you replace it with a lot of other things, it's not going to really impact too much. The thing that is very important there is that you need to have the gradient of logarithm of your policy, or gradient of the log likelihood. Yeah? This is gradient policy theorem. So it says that whatever you want, whenever you want to update your policy network, whatever you use, right? Whatever algorithm you use, how complicated you do it, it's not important. The thing that should show up here, which is going to update your parameter, should be proportional to the gradient of the log likelihood. And this is one thing that I want to just show next. So now the